Welcome back. In today's lecture, I am going to talk about the Euler Lagrange equation. Okay. So far, what I have discussed that how to do modeling based on first principle. Okay. And basic idea is that try to observe some kind of law which is follow from the large class of system in the condition of parameter variations. Okay, so suppose that I have resistor, and what we have observed that if I am going to change the resistor, okay, so I have R1, I have R2, I have Rn, something like that, and I am going to apply different voltage across this, and after that I have formulated some kind of law. Okay, and what we found that even if you can vary the resistance R1, R2, R3, the current and voltage has certain kind of properties. Okay, similar kind of observation, suppose that I have some kind of mass, I will apply some kind of force, and after that I have some kind of acceleration that is associated with that. Okay, after that similar kind of things we have observed. Suppose we have certain kind of a spring, we have applied some kind of force, and after that I have certain kind of displacement. Then what is relation between force and displacement? Okay, so based on several experiment, finally we'll end up to the certain law, and after that what we are doing that either some kind of conservation of energy, or conservation of mass, or conservation of charge, we are going to formulate some set of differential equation. Okay, so that is the very basic idea of the modeling of dynamical system. Okay, now in the second part of this course I am going to talk about the modeling based on the energy principle or energy based modeling. Okay, and it is possible to show that energy based modeling is more economical or more applicable for very complex system. Okay, so modeling by first principle when complex system, then that become very difficult to model. Okay, difficult to write differential equation of all subsystem and after that connect it. Okay, but Euler Lagrange way, or somehow you can think like I will introduce some new notion that is called variational calculus. Okay, so using the help of variational calculus, it is possible to show that if you know the kinetic energy or potential energy of some system, suppose you have mechanical system, okay, then based on that I can able to formulate directly the differential equation. Okay, and that is also independent of the coordinate system. That is the another beauty of that. Here whenever you are doing energy based modeling, so that is heavily dependent on the choice of coordinate system and choice of frame. Okay, we have already seen that. Now suppose if you have electrical system, so by analogy we have seen that whenever I have capacitor, so capacitor is going to store energy in form of the potential energy. Similarly inductor in form of kinetic energy. Again I can formulate similar kind of law. So by analogy it is possible to show that I can define energy, kinetic energy like quantity and potential energy like quantity, and again I can able to do the energy based model. Okay, and energy based model later part you are able to see that even system is very complicated, you are able to formulate the energy based model. Okay, so between first order modeling based on first principle and energy based modeling, I have also talked about the some part of linear algebra. Okay, and what we observe that in linear algebra we have notion of vector space, notion of non-linear space, notion of inner product space, and after that in previous class I have talked about the convergence, continuity and transformation. Okay, so and what we have observed that whenever we are dealing with any dynamical system, then I have different spaces. Okay, so I have some quantity is going to lie or represent in form of column space. Okay, so where each element in form of column, some kind of a space where element is in form of functions, and some kind of a space where element in form of matrices. Okay, so we are going to involve that kind of things also in today's formulation. Okay, so if you don't have a crystal clear idea of the linear algebra, it is difficult to follow or appreciate the today's lecture, and due to that reason you are able to see that I have given a lot of time towards the linear algebra. Okay, so let us start the today's lecture. So I am going to talk about, in today's lecture I am going to talk about calculus of variation. Okay, with help of calculus of variation it is possible to formulate Euler Lagrange equation, and using Euler Lagrange equation I can able to talk about the mathematical modeling of the dynamical system. That is the basic idea. Okay, so if you see the calculus of variation, and this calculus of variation is basically introduced by the another group of people which is working towards the calculus. If you see the history, then history who has developed the calculus, that is still not clear. Okay, some people are telling that Newton has developed calculus, another group of people are arguing that actually Lagrange has developed the calculus. Okay, so we have certain kind of actually some kind of biasing happens, and energy based approach or calculus of variation based approach becomes suppressed for a long time. Okay, it become popular when Einstein has given the theory of relativity. Okay, and then people are able to see the beauty of the calculus of variation. Okay, actually law of the theory of relativity is still not going to change whenever we are going to use the calculus of variation. Okay, so actually Einstein has shown that calculus of variation is more consistent, okay, with the theory of relativity, and then people start appreciating it. Okay, so let us try to see what is meaning of calculus of variation. So the calculus of variation is concerned with the extremal of the functions whose domain is a infinite dimensional space. You can see that again spaces are involved here. So suppose that if you don't have knowledge of the vector space, then you are not able to understand what I have written here. Okay, so try to understand in layman language. Suppose I have some quantity x. Okay, you can assume that x belongs to R, and based on x belongs to R I have defined something fx. Okay, so I have some kind of domain, and domain is nothing but some kind of real number, and based on that domain I have defined some function. Okay, now even if I have x belongs to Rn, I can still define some kind of function that map from Rn to R. Okay, so I can define fx, and I am assuming that still that belongs to R, so it means that f is going to map from Rn to R. Okay, so what happens in you can think like this. I have some function in two-dimensional space. I have some kind of function which is function of x1 and x2, and that is going to give some kind of value that is just a real number. Okay, so here I can tell that I have some kind of function in n-dimensional space. Okay, and where argument is column vector that is going to map to some kind of real number. Okay, now in previous class we have actually learned about another kind of function where argument is again some kind of function. Okay, and actually that kind of function in this particular lecture I am going to represent by phi. If you see the literature, then people may represent by j also. Okay, so what we are telling that jy or phi y you can take, or phi, whatever symbol I am using, same symbol phi gamma you can see here. So basically now here argument is not a column vector, that is some function. Okay, so basically now what kind of function we are going to talk about? Functions of functions. Okay, and that is called functional. Okay, so are you able to understand the difference between simple function and function of function? So I have two things. I have function and I have functional. Okay, so both, it is possible to show that whenever I am talking about some kind of function, it means that I am going to talk about some kind of transformation. So whenever we concentrated on functional, that is very special class of transformation where argument is function but that map to some kind of real number. Okay, it might possible I have some kind of function that map from Rn to Rn also. Okay, whenever I am writing x dot equal to fx, okay, and x belongs to Rn, during the definition of autonomous system, you might have seen that I am writing like this, Rn map to Rn. Okay, so this is called some kind of function. Okay, I have some special class of function here also, that f map from Rn to R. Okay, but argument is still some kind of element that is coming from finite dimensional space. Okay, it means that I have n tuples of the vector and each vector is some kind of real number. Okay, now here whenever I am talking about calculus of variation, at that time we are going to define some kind of function where argument is also function, and we know that whenever argument is function, function is nothing but they have basis, and inside the basis we have infinite many elements. Try to understand this part just by taking some kind of continuous function, continuously differentiable function. So I can able to do Taylor series expansion. Okay, and infinite many term I have inside the Taylor series expansion. So dimension here, that is infinity. Okay, so whenever we are talking about calculus of variation, now I think that things become clear. I am going to consider the function of function, and since function has infinite dimensional argument, okay, so that is different from the classical function. Okay, now another thing, you can see that I have used one word, that is extremal. Okay, that is just parallel to minimization or you can tell that maximization. Okay, so suppose that during school time, what we have seen, that I have some kind of function, you can take any function. So this point is some kind of minima. Okay, so I have x and I have fx. So we are defining minima of this point provided value of this fx is minimal. Okay, in some interval like 0 to x you can take, or 0 to y you can take, that in this interval I am looking towards the function and this value is minimal. Okay, now I have two things. It might possible if I have some kind of function, now you can change the function. So at some interval I have maxima, some interval I have minima, that is local maxima, local minima. Okay, so we are solving the maximization or minimization problem, that is also called optimization problem. Okay, so we are talking about optimization, means that is concerned about maxima and minima. Similarly, now I have some kind of function, and function is again function of function, that is called functional. So at that time again I am going to talk about maxima and minima, that is called extremal. Extremal means either maxima or minima. Okay, so terminology is just actually this kind of terminology used in variational calculus, that is actually introduced by Lagrange. Due to that reason, that kind of terminology and this kind of terminology, that maxima and minima, that is introduced by Newton. Okay, and so just we are going to correlate those two terminology. Okay, now let us try to see the example of functional. Okay, so simplest example of functional, suppose you have two-dimensional curve. Okay, so in two dimension, suppose I have some kind of curve, I want to calculate the length of this curve. Okay, so you can see that here I have, you can assume that I have x and here I have y, something like this. Okay, if this is a straight line, then it is very easy to calculate the length of curve. Okay, but this is no longer a straight line. Okay, so how to calculate the length of curve? What you can do, you can take the piecewise curve, okay, and after that you can integrate from here to here over all length. From here to here you can integrate it. Okay, so it means that if you consider very small length, at that time length I can write like this, dx square plus dy square and a square root of this. Okay, now what I will do, I will take the common of dx square and then I can write that dy by dx dy square, or like this also you can write, and after that I can take dx out. Okay, and after that what I will do, independent argument, suppose that is t0 to t1, so I am going to integrate whole things by t0 to t1. Okay, and after that dy by dx you can give some kind of symbol, so I have given x dot. Okay, so x dot, either you can suppose that this curve is formulated between t and x, then you can write x dot. Okay, so suppose in place of x, now I replace by t, in place of y I replace by x. Okay, then I can write this length from here to here, that is dx by dt. Anyone has confusion? So this whole s can be written like this. Okay, anyone has confusion, then please let me know. So what I am telling, that I have some kind of curve in Euclidean plane, and using Euclidean norm, okay, with help of Euclidean norm I am going to calculate the distance from here to here in this curve. Okay, so piecewise you can cut it and after that integrate from here to here. So now try to see this curve carefully. Okay, here what happens, if you see x, so x is itself vary with t. Okay, so here if you see the t is some kind of real number and that map to x, so this is function. Okay, now x dot also, that is actually function of t, so that is varying based on t, so again this is function. Now if you see phi and here gamma, so phi gamma is basically now they have two arguments, so that is direct function of x dot. Okay, and x dot is function of t, so it means that phi gamma is function of the function. Okay, so that is called functional. Now try to see that this is going to map to one dimension or not. So x belongs to r, I am assuming, and x dot obviously derivative also belongs to r. Due to that reason this is going to map to one dimension. Anyone has confusion? And due to that reason I have written here, in general a functional is any mapping from a space of curve to a real number. Okay, now you can take 2 dimension, 3 dimension, any dimension. Okay, just you have to make sure that their argument should be function. Okay, and function might be infinite dimensional function, and after that map to some kind of real number. Okay, in this way I can able to define the functional. Okay, now I hope that difference between function and functional become clear. In previous class I had, during transformation I have also talked about, I have told that I am going to talk about very special class of function that is going to map from some vector space to one dimensional real number, means again that is vector space, and where field element is real, and after that what you can do, you can try to understand addition and multiplication of the real number. Okay, so now I have any function that is going to map to the real number. Okay, and this is called functional. Okay, function of function. Now let us come to the definition of variation. Okay, so I hope that the definition of functional become clear. So since I am talking about functional of function of function, that is called functional. Okay, now one more important point you have to here try to understand, that if I minimize this function fx belongs to r, or fx if that map from Rn to R, so suppose that if this point is the minimum point, so x is column vector. If x is column vector, so that is finite dimensional point. Okay, suppose x is Rn, So I have n tuples of number, and at that point function has minima or maxima. But here what happens, that if you are going to extremize some kind of functional, at that time this y is nothing but again coming from infinite dimensional space, some kind of function. Okay, so if you are going to minimize some kind of functional, then you are going to get some kind of function. Okay, now one more important point I am going to highlight here. You might have seen that whenever I have differential equation, then their solution is nothing but some kind of function. Okay, so what I am going to do now, I am going to define some kind of functional, and after that I am going to extremize it. So I am going to get some kind of function only, and try to see that function is actually coming from some kind of differential equation. Okay, I will highlight this point in the next part of the lecture. Before that, first try to understand what is meaning of variation. Okay, variation is nothing but some kind of approximation. Okay, so in order to define the variation, what I am going to do, I am going to first try to see that I have some kind of curve. Okay, so curve I have, suppose this curve gamma curve, and nearby of gamma curve I have again defined some gamma dash. Okay, in the previous class I have told you that whenever I am going to talk about maxima and minima, at that time I need two things. Okay, suppose that this is the maximum point, okay, minimum point, and this is the maximum point. So I have to give guarantee that all point, if I substitute inside this function, okay, so this value is least among all, and similarly this value is maximum among all. Okay, so it means that I have to travel from here to here, and every time I have to check it. Okay, similarly this is a story about the minimization of function or maximization of function. If we are going to talk about functional, so what we have seen, that argument of some kind of functional is function, or phi gamma we are writing. So gamma is nothing but some kind of functional. So if you are going to minimize this, then you are going to get some kind of nearby function only. Okay, and due to that reason, you can see that whenever I am talking about variation, at that time I am assuming that I have some function gamma, and nearby of gamma I have something like gamma dash. Okay, so that kind of things is required whenever we are going to formulate this kind of problem, that we want to show that I have some kind of initial function gamma and their approximation of gamma dash. Okay, and I can able to define gamma dash like this, since here gamma is function of x and t. So what I am telling, that now gamma dash is xt plus ht. Okay, and here gamma dash is nothing but gamma plus h. Okay, so variation in h, and after that I am going to define the increment. And how to define the increment? I know the function gamma, I know the function gamma plus h. Now I am going to put or keep that function inside the functional argument, because whenever I am going to talk about some kind of functional, so their argument is function. So I know one function, that is gamma. I have defined gamma dash. Gamma dash is nothing but gamma plus h, that I am going to keep inside this. And after that, now definition of differential comes into picture. So basically what this definition is suggesting, a functional phi. So functional means function of function, is called differential if phi gamma plus h minus phi gamma equal to f plus r. Okay, and here you try to see that what I am telling, that this f is going to satisfy two property. Okay, so two property is, this is called property of additivity, and this is called property of homogeneity. Okay, so this part is going to follow the principle of linear transformation. Okay, so what basically we are telling, that whenever we are defining this increment, after that I am going to collect those kind of term which will follow these two property. Okay, in another word, try to understand the meaning of this. Suppose that I have some curve like this, okay, and I want to calculate the derivative here. So what is physical interpretation of derivative? That tangent at this point. Okay, now suppose we are in two-dimensional space, okay, like this. So what is interpretation of physical derivative here? Anyone, could you please comment? In two-dimensional space, I have already told this kind of interpretation when I have started this course.
Disk.
What?
Disk.
Could you please try to define in terms of linear algebra? So here you can see that I am approximating this point with respect to some kind of line. Okay, so here it might possible you can tell that as a disk, okay, but that is not going to give us any idea. Okay, so what basically we are telling here, there exists some kind of linear transformation here, linear approximation here, okay, and that linear approximation is going to best fit here, okay, and that is interpretation of the derivative. Okay, and you know that what kind of property linear transformation is going to satisfy? Two property, additivity and homogeneity. In previous class I have introduced that. So physical interpretation of derivative in higher dimensional space is we are going to find some kind of best fit linear transformation at certain point. Anyone has confusion? Similarly, now if in place of the t you are going to replace by function, okay, so again I am going to find some kind of linear transformation only. Okay, so whatever linear transformation that comes into picture, that should satisfy these two property of the additivity and property of the homogeneity. And after that we are going to consider the higher order term. Okay, so higher order term I have written like this. Okay, and I am assuming that higher order term is less dominant over this term f. Okay, then only we can tell that this at this point this particular transformation acts like some kind of differential or derivative, we can tell. Okay, so linear part of increment fh is called differential. So how to calculate differential? What you can do, if you have some kind of functional, so take the increment in the independent quantity. So independent quantity is nothing but some kind of function. So I have taken the increment in function, and after that I am going to keep the difference between original function phi y and incremented function. Okay, and after solving phi gamma plus h minus phi gamma, I am going to collect those kind of terms which will satisfy these two property, and that property is called differential. Anyone has confusion? Okay, now let us try to understand what is meaning of variation. So it can be shown that phi is differential and its differential is uniquely defined. Okay, so whenever you are going to talk about the differential of some curve at certain point here, and if it is possible to show that only one type of curve may be any, might be disk or anything else. Okay, so higher dimensional structure, some kind of higher dimensional structure. Okay, so that will satisfy these two property, and only unique curve exists there. So I am not going to prove that. Okay, so same like at this point I have unique tangent, similar kind of things is here, that only one curve which will satisfy this kind of property is there. Okay, and due to that reason you can see that same kind of point I have written here, and this differential of function is called the variation, and h is called the variation of the curve. Okay, so variation is nothing but some kind of differential. Okay, so now how to calculate variation? Whenever I have some functional, I will take the increment. Okay, and that increment is now called variation. Okay, and after that what I will do, I will try to calculate this, and out of this, after doing Taylor series expansion, what I am going to do, I am going to collect the linear part. Okay, and it is possible to show that that is nothing but some kind of Jacobian only. Okay, we will solve some exercise, then it become little more clear. Okay, now let us try to see with example. So again I am going to repeat with same example, because whenever I am in two-dimensional space and here t and x, what we found that length of curve from here to here, that is going to give in the form of 1 plus x dot square. Okay, and integration from t0 to t, this is t0 and this is t1 you can take, and this is nothing but dx you can take. Okay, something like that. So now here dt, here whenever I'm integrating from t0 to t1, that is dt. Okay, so now I can define functional in more general way. What I am telling here in this particular example, inside this x dot only came, but generalized one it might possible inside this I have some kind of functional. Okay, and here L is general length you can tell, that is function of x dot and t. Okay, so this is the generalized definition of the functional. Okay, so whenever I am in two-dimensional space, so functional I can define with the help of independent variable, dependent variable and their derivative. Okay, suppose now if you are in two-dimensional space, okay, here two-dimensional space, three-dimensional space, then one more quantity yt comes into picture, and at that time yt and y dot t also involved. We will see that kind of generalization. So this is the definition of the general functional. Okay, anyone has confusion? Okay, now let us come to the theorem. Okay, so now what this theorem is telling, that functional phi y then is differentiable and its derivative is given by this formula. Okay, so if you have this kind of functional, okay, so is differentiable means I am assuming that whatever functional I have constructed that is differentiable, then derivative can given like this. Okay, let us try to see. So how to calculate differential? We have just seen in definition that in order to calculate the differential of some quantity, what I have to do, I have to take the increment of that. So I have this kind of functional phi gamma t0 to t lx x dot t dt. So I have taken the increment, and after taking the increment, what I am going to do, I am going to do the Taylor series expansion. Okay, so if you do the Taylor series expansion of this, so one quantity is lx x dot and t, first quantity, and you can see that similar quantity I have subtracted here, so that is going to become cancel out. Okay, what is second term? That is variation of L or differential of L, partial derivative of L with respect to x. Okay, because here I have two terms, x and x dot. So one time I am going to see what of effect if I vary x and x dot is constant. Okay, so at this time, if you see the variation of x, then I have x plus h minus x, and due to that reason h comes into picture. And similarly with respect to x dot, so again x plus x dot plus h dot minus x dot, so h dot, and after that I am going to collect all higher order term. Okay, so now what I am going to do, I am going to write this as a fh plus r. Okay, and it is possible to show that this part, whatever part I have written like this can satisfy the property of linear transformation. Okay, so please check it by yourself. And after that, what I am going to do now, I am going to use the formula of integral by part. Okay, so by using the formula of integral by part, it is possible to show that this term dou L by dou x dot h dot dt, somehow I am going to remove h dot. Okay, because increment is h, so I am not try to care about h dot. Okay, due to that reason somehow I am going to remove this. Okay, so I have used the integral by part, and after that if you substitute this here, then it is possible to show that actually this expression comes into picture. So same kind of things I have written. Anyone has confusion? Okay, so best way is that what you can do, you can take your copy and pen and try to drive it. Okay, and after that if you find that something is missing, then please discuss with me. Okay, now what I am telling, that the extremal of a differential function phi y is a curve gamma such that fh equal to 0 for all h. Okay, so here what I am going to do, I am not going to prove. Okay, what I am going to do, I am going to take the help of finite dimensional optimization problem. Okay, so what we found, that in finite dimensional optimization problem, if I have some kind of function, so in order to calculate maxima and minima, so maxima and minima or a stationary point exist if f dash x equal to 0. Okay, similar kind of things here I am telling, that if extremal of some functional comes into picture, at that time differential or variation equal to 0. fh is variation because differential is called variation. So that variational is equal to 0. Okay, so now let us try to see the next theorem. Okay, so based on all previous theorem, now I am going to define some concrete result, and result is like this. Suppose you have some kind of curve gamma and extremal of the function. Extremal means I am going to talk about maxima and minima both. I am not worrying about either this is maxima or minima. Okay, so I have taken this kind of function, and now what I am telling, that suppose I have some kind of, first you can think like I have two-dimensional space t and xt. Okay, in this space I have some kind of curve, and here this point is t0 and here this point is t1. Okay, now corresponding to this point I have xt0 and xt1. Okay, now what I am going to do, I am going to find some kind of curve between these two. So you can see that infinite many curve is going to join from these 2 points. Okay, now out of this all curve I am going to find the extremal curve. It is possible to show that whenever extremal curve comes into picture, that will satisfy this relation. Okay, so curve means I have some kind of functional phi that associated with this curve, and functional is, here you can see that gamma is function of x and x dot and t. Okay, so curve joining from here to here, so these 2 points are fixed. Okay, so if these 2 points are fixed, it is possible to show that variation of this point with respect to t0, that is 0, with respect to t1, that is 0, xt1, that is 0, and xt0 is 0. So curve between these two, so end point, these two are always fixed. So fixed means there is no variation, but I have variation of this curve, and among of that I am going to select the extremal. Okay, extremal means you can think like maximum and minimum. Okay, and if that exists, then that will satisfy this kind of equation. Anyone has confusion? Okay, now let us try to prove this theorem. So in order to prove this theorem, I need one lemma. One small result is called, whenever I have to prove big result, sometimes some small result is required. So what this small result is suggesting, that if a continuous function ft between t0 to t1. Okay, so suppose that you have some continuous function between t0 to t1, and if that will satisfy this kind of condition ft ht, so you have function and you can multiply this function ft with another function, and suppose that this function ht has property that ht0 and ht1 equal to 0, then it is possible to show, and you know that this is also equal to 0, then I have only one option, that ft equal to 0. Okay, so what I am telling, that I have any continuous function ft, and after that I have, that is multiply with ht, and after that integral of this to this t0 to t1, that equal to 0 I know, and I also know that at ht0 and ht1 that equal to 0. Okay, then I have just one option, that ft equal to 0, that kind of lemma, and proof is not so difficult. what you can do, you can assume that ft is not 0 always, some interval that is non-zero. Okay, and if due to that reason I am assuming that ft star is greater than 0 for this interval, some interval t star that is greater than 0, and after that ft is continuous. So when something is continuous, then we know from the definition of continuity that, suppose in previous class I have told you that if some function is continuous, then you have to form the ball on the image space, and corresponding to that you have to see that there exists some ball like this. Okay, so there exists some kind of neighborhood here such that if their mapping lie in this ball, then I can give guarantee that that will lie in this ball. Due to that reason I have considered this neighborhood. Okay, and after that what I am going to do, I am assuming that let ht be such that ht equal to 0 outside this neighborhood, but that is non-zero outside this, and ft I have from the property of continuity. So if t is going to lie, then that is going to map to some number. So ft is some kind of number, suppose that number is d, and ht has some kind of number. You can write that t0 minus t, here t0 minus t, that is I have assumed that is 1. So t0 minus t I have defined whatever this interval that I have defined as a c. So it is possible to see that that is always greater than 0. It means that whenever I assume that ft star is greater than 0 in any interval, then what happens that I cannot able to get integral of multiplication of integral equal to 0. Okay, so by proof of the contradiction, I can tell that ft has no other choice that equal to 0. So in mathematics, what is beauty? Either things are true or false. Okay, so somehow if you are able to generate some kind of contradiction by taking ft greater than 0, so I have another only one option, that ft equal to 0. Okay, another way what you can do now, you can assume ft star less than 0. So again some negative number comes into picture. Okay, so due to that reason, whenever I have this kind of relation, then only I have one option, that is ft equal to 0. Okay, so why we are taking help of lemma? It is actually evident from here. Okay, so what we have seen that integral, you can see that if I have defined the variation, at that time variational of this is given like this. Okay, and I know that ht1 and ht0 both are 0. Okay, so this is automatically 0. So I have some kind of function here and h equal to 0, and I know whenever variation comes into picture that equal to 0. So finally I will get up with this result. Okay, so same kind of things I have actually, same way I have proved here. Okay, so using this kind of lemma. So again I have first way I have calculate the variation. Okay, and after calculating the variational, what I am going to do now, since ht0 and ht1 equal to 0, so variation, because whatever curve I have constructed, I am assuming that these two curves are always passed through this, so there is no variation here. It might possibly in between I have variation, but there is no variation at these 2 points. Due to that reason, ht0 and ht1 equal to 0. Okay, now ht0 and ht1 equal to 0. So if you put this t1 and t0, limit ht1 and ht0, so that equal to 0. So this term is equal to 0. Okay, now what happens that I have same kind of situation like this theorem. Okay, I have to show that there exists extremal. It means that this should be 0. If this should be 0, now I have situation like I have some function. You can think this function as a f t, and I have some kind of function ht and dt, and I have condition like these two. Okay, and integral of this equal to 0 whenever I am asking for the extremal. So I have only one option, that ft equal to 0. So same way I have proved this theorem. Okay, so theorem is like this theorem. So what theorem is telling that if some curve gamma xt, whenever we are defining some kind of functional, that is function of function, so if we are going to talk about extremal, then either that is maxima or minima, that will always satisfy this kind of equation. Okay, and now since this equation is always satisfied in case of maxima and minima, and due to that reason I am going to give a special name to this. Okay, and that is called Euler Lagrange equation. Okay, so now let us try to see that suppose I am in two-dimensional space. Okay, and in this two-dimensional space I have 2 points. Okay, and what I am going to search, that what is extremal curve between here to here. Okay, between these two. So that might be like this, like this, like this, like anything, I don't know. Okay, now what I am going to do, I am going to derive the equation of that extremal curve. It is possible to show that extremal of length are a straight line only. Okay, so how to prove that? Again, what you can do, you can collect the inside the functional, you can see that t0 to t1, and after that I have L and that is function of x dot and t. Okay, and dt. In case of this curve, what we have found, that L is nothing but 1 plus x dot square. So same kind of things I have taken here. Now whenever some extremal happens, just now what kind of relation we have derived, that d by dt dou L by dou x dot minus dou L by dou x equal to 0. Okay, so what I am going to do, I am going to calculate dou L by dou x. So since this is just function of x, due to that reason that is 0. This is function of x dot, so just you can calculate the partial derivative with respect to x dot, then you can do this. So this is very simple calculation, and after that you can do d by dt of this. Okay, and after if you do x and x dot, so this is derivative, so you can take integral both sides. Due to that reason some constant comes into picture, and it is possible to show that x dot is only c1, and if you see x, then that becomes c1 and c2. So this is the straight line. Okay, so extremal curve that is going to join in two-dimensional plane, that is a straight line. In this way you can able to show. Okay, so now what is meaning of now what is the name of this equation? Okay, so what we found, that I have some space. Okay, and in a space I have some function. With help of function I have defined functional. So that functional is contain the extremal value. Okay, and that will always satisfy this equation, and due to that reason we have to give some kind of a special name. And actually this kind of calculus is worked by Lagrange, and Euler, Lagrange, all are very much connected. I don't remember who is a student of whom, but one of people is a student of other, like that. Okay, so Euler Lagrange equation and functional is one can define like this. Now I can also generalize this. Suppose that if I am in n-dimensional space. Okay, so n-dimensional space means I am in Rn. Okay, and here I have x. So x is now element is like function x1t, x2t, xnt, like this. So x1 belongs to x1 is some function, and that belongs to some real number. X2 is function, some belongs to real number. But here you can see that t is also varying. So that is little bit different from column vector, because here each entry is some kind of number, but here automatically number is going to come into picture, but each and every time number is changing. That is the difference. Okay, so now what I am telling, that let x be vector in n-dimensional coordinate space, and I have some kind of curve in higher dimensional space. Okay, so I have n plus 1 dimension. Why n plus 1 dimension? We have just seen that if I have some curve, x curve, so one independent variable is required. Okay, so due to extra addition of one independent variable, if I am going to talk about x, then that is finally come into two dimension. Okay, suppose if you have two dimension x1 and x2, then again one extra variable, independent variable time comes into picture. Due to that reason I have retained the dimension is n plus 1. Okay, Lagrange, you can see that I have retained that is dimension is equal to 2n plus 1. Why? because what we found that Lagrangian is function of x dot and t. Okay, so x is belongs to Rn, x dot belongs to Rn because derivative belongs, and this is belongs to R1. So n plus 1. So due to that region 2n plus 1. Okay, so now functional I am going to define, that is actually now 2n plus 1 dimension, and that finally map to 1 dimension only, because I am going to talk about the functional, and that should be mapped to some kind of real number, function of function. Okay, and it is possible to show now that in case of the Euler Lagrange equation, it is possible to show that if you solve this is second order equation. Okay, so now second order equation, now I have nth order system. So for if I am just going to talk about one dimensional curve, okay, that is lie in 2 dimension, then I have second order equation. So I have now, suppose that I have x variable that is going to lie in Rn, so total number of equation is 2n. So similar kind of things I have written. Okay, so corresponding, suppose that this is t and x, and if you define any functional, that is function of x dot and t, then whatever Lagrange equation or Euler Lagrange equation comes into picture, that is order of 2. Now suppose this x is increased to Rn. Okay, due to that reason this is also increased to 2n. Okay, so when I will take some physical system and solve Euler Lagrange equation, then I will show you why that is 2n. Okay, now you can see that one of the important remark is that extremal curve is independent of coordinate system. So now you can consider any polar coordinate system or any other coordinate system, it is always possible to show that again that will satisfy the Euler Lagrange equation. And due to that reason, what is beauty, that whenever you are going to do mathematical modeling with Euler Lagrange equation, then there is no need to worry about the coordinate system, choice of coordinate system. Okay, always that will satisfy. One gap is still remaining, that I haven't tell you, that how basically mathematical modeling is related with the Euler Lagrange equation. Okay, so what happens, what we have seen, that I have some kind of physical system, and physical system is evolving. Okay, so what is nature? Suppose that if I have autonomous system, it is possible to show that if autonomous system travel from this point to this point, so they want to expend minimum amount of energy. Okay, and they want to maximize their process. Okay, so always maximization and minimization occur inside the nature. Okay, so what we are telling that, and whenever we are talking about dynamical system, we are just trying to see that how basically system is evolving. Okay, so Euler Lagrange is telling that system is evolving in optimal way, because that is proven fact. And due to that reasons, if system is evolving in some kind of optimal way, so that curve should satisfy the Euler Lagrange equation. And due to that reason, whenever you have some kind of autonomous system, for non-autonomous case I have some modification is required. So here some right hand side I have some modification, we will discuss in the next class. Okay, so if I have autonomous system, then automatically whatever trajectory that is generated by this system, physical system, that will satisfy the Euler Lagrange equation. I hope that you are able to understand the motivation. Motivation is that whenever some physical system is evolving in this space, okay, any physical system, that is going to satisfy the principle of extremization. And whenever I have extremization, means minimum or maximum, so that will satisfy this Euler Lagrange equation. We have proved mathematically, and due to that reason, if you just solve this equation, then you can get the dynamical equation of the system. Okay, so let us try to see that how to get dynamical equation of the system, what is relation with the Newton's equation. Okay, so here we indicate the variational principle whose extremal are solution of Newton equation. It means that Newton equation is very just a special case of Euler Lagrange equation. Okay, so if you see the Newton's equation, what basically we are doing, we are trying to write F equal to ma, some kind of formulation like this. Okay, and here similar kind of things I have written. R, you can assume that some kind of position vector, r dot is the velocity vector, and d by dt mi you can take the constant. So this is nothing but force, or ma, you can write that this term ma. Okay, and it is possible to show that force if you know the potential energy, and if you differentiate potential energy with respect to r, then that will give you the force. Okay, now I am going to actually correlate this with this. Okay, so from here you can see that from these two I can able to write like this. Comparison I can write like this. What I am going to do now, I am going to formulate some kind of functional, and here this L, whatever curve I am telling, curve, now L I am going to define the difference between kinetic energy minus potential energy. Okay, and after that I am going to solve the Euler Lagrange equation. Okay, so now whenever I am talking about kinetic energy, so kinetic energy is actually associated with the rate of change of motion. Okay, within 5 minutes I will complete this class, and due to that reason kinetic energy I have written mi/ri dot square by 2. Potential energy is just due to a state of means some kind of physical state, and due to that reason that is function of r. So if you calculate dou L by dou r dot, then only this term comes into picture, dou t by dou r dot and mir dot comes into picture. Here that is function of r, so dou L by dou r dot minus du by dr dot. Okay, so it means that if you just replace dou L by dou r dot by this, and dou L by dou r dot by dou u by dou r dot, then what happens that you are exactly able to get the Euler equation, from the Euler equation the Newton's equation. Okay, and here you have to define L. L is nothing but kinetic energy minus potential energy. So basically what I mean to say, that whenever some physical system is evolving, they try to minimize or extremize this difference, not minimize, they try to extremize, because sometimes extrema minima, sometimes maxima. Later people has shown that that is minima only. Okay, I will discuss that. Okay, so what happens whenever some physical system is evolving, they try to minimize this functional that is generated from kinetic energy minus potential energy. And how to define functional I can define from t0 to t and L and dt like this. Okay, then exactly I can get same equation like the Newton's equation. Okay, so there is no need to worry about now Newton's equation, just you can calculate the kinetic energy, potential energy, and take the difference. Okay, you can use any coordinate system, because Euler Lagrange equation is also independent of the coordinate system, so that is independent of same kind of. Another thing is the Hamiltonian principle of least action. I have told you that whenever some system is evolving, some autonomous system is evolving, so they try to minimize the action they have defined, because you can see that this is not a total energy. That is the difference between kinetic energy minus potential energy. Total energy is kinetic energy plus potential energy, but what Euler Lagrange has formulated, that system try to minimize the gap of kinetic energy minus potential energy. Okay, and due to that reason they have given name as a action. Okay, so due to that reason this principle become the Hamiltonian principle of least action. Actually this things is actually highlighted by the Hamiltonian. Okay, so in mechanics we use the following terminology. So how to formulate L? You have to take Lagrangian function, that is called Lagrangian function or Lagrange. Okay, so now you can, whenever you are solving the maximum extremization of this functional, now there is no need to worry about the whole things, just you can worry about the Lagrangian. And how to define the Lagrangian? Kinetic energy minus potential energy. Okay, and after that now you can see that whenever I am talking about if you see the Newton's second law carefully, then we are telling that rate of change of momentum equal to force. Okay, and due to that reason first term is nothing but the generalized momentum. Okay, and force dou L by dou Q will give you the force. Okay, and this is called the action. Okay, and after that this equation will satisfy. So last theorem is called Hamiltonian form of the principle of least motion, because in many cases the action qt is not only an extremal but also minimal. Okay, extremal means maximum and minimum. So how basically nature are evolving, they try to minimize the action functional. Action functional, and what is meaning of action function? That is the difference between kinetic energy. Okay, so it means that during the mathematical model, now we know that physical system try to minimize the action functional, and how to define action functional? Kinetic energy minus potential energy. Okay, so somehow I will formulate kinetic energy minus potential energy, and after that what I am going to do, I am going to solve this partial differential equation, dou L by dou x equal to 0, and by solving this I will get the equation of motion of this autonomous system. Okay, whenever I have non-autonomous, some more modification is required. Okay, we will discuss about that modification, because you can see that here generalized force, so I have to add something whenever some extra force comes into picture. So same as whenever we are dealing with the Newton's law, you might have seen that whenever I have extra force, then we are going to add the opposite of that extra force, such that actually inertial frame, non-inertial frame is converted into inertial frame. Same kind of modification I am also going to do here. Okay, so now it is time to conclude the today's lecture. What we have found in today's lecture, that if I have some kind of autonomous system, okay, and what is beauty of the system, that somehow whenever system is evolving, they are generating some kind of trajectory. Okay, so during the generation of trajectory, they are going to minimize the action function. Okay, and action function is nothing but that is Lagrangian. Okay, so by solving Euler Lagrange equation, I can able to do the mathematical model of the physical system. Okay, now lecture is in from my side. If you have any question, then please let me know.